Hi everyone, my name is Robert Lyerly. I'll be presenting the work Dynamic and Secure Memory Transformation in Userspace. This work was done at Virginia Tech along with Xiaoguang Wang and Binoy Ravindran. In this presentation, I'll start by introducing the problem of defending against stack-based exploits. I'll then describe the design and implementation of a new framework called Chameleon. I'll go through the evaluation of Chameleon, including its ability to generate highly randomized stack slot locations and generating this with very low overhead. And finally, I'll conclude the presentation. So let's start by introducing the problem. Memory corruption is still one of the biggest threats to software security. So for applications written in native languages like C and C++, it's still possible for attackers to exploit buffer overflows or redirect pointers and references to arbitrary locations in memory in order to attack vulnerable applications. The security community is still crafting new return-oriented programming style attacks, which reuse existing code and stack locations to attack target applications. Here's an example of a return-oriented programming style attack. So an attacker has used an overflowed buffer in order to pre-populate the stack with certain handcrafted pieces of data in order to attack the application. So in particular, the attacker has inserted return addresses on the stack, which return to certain gadgets inside the application's existing code, which perform little snippets of functionality. So in this particular example, the attacker has inserted returns to gadgets which pre-populate certain registers with certain values. The final piece of this chain is a return into improtect in order to change the mapping of some piece of memory in order to make it readable, writable, and executable. This gives the attacker the ability to inject arbitrary code into the target application's address space and then perform arbitrary functionality. Recent works describe new attacks which reuse existing data on the stack in order to work around existing defenses. In particular, position-independent return-oriented programming and data-oriented programming use data on the stack in order to attack applications. In this figure on the right-hand side, we show an example of PyROP stack massaging. So the application calls a certain chain of functions, and as it returns back from those functions, it leaves existing data on the stack. The attacker patches that existing data, called massaging that data, in order to instead point the application to arbitrary gadgets inside and then execute an attack inside the application. So this is very hard to detect and hard for applications to defend. Existing frameworks disrupt ROP attacks by randomizing or hiding the application's memory layout. Several examples of existing frameworks include Shuffler, Redactor, Isomeron, and Smokestack. All of these defenses have one or more of the following problems. First, they don't defend the stack, which means the applications are still susceptible to the previously mentioned stack-based exploits. Second, they either inject code via dynamic binary instrumentation, or they force extra redirection, which can create huge resource overhead. So for example, it can add anywhere from 10 to 15% extra CPU overhead and as high as 50% memory overhead. So this can cause lots of problems in production environments. In this work, we present Chameleon, which is a novel framework that continuously re-randomizes the stack to disrupt these aforementioned stack-based attacks. Chameleon randomizes all function stack frames, including permuting the ordering and inserting padding between stack objects. Chameleon also rewrites each function's code to match the randomized layout. This has a knock-on effect of disrupting ROP gadgets, further preventing attackers from targeting vulnerable applications. Finally, Chameleon is novel in that it is an out-of-band framework. It attaches to target applications from an entirely separate process using existing OS primitives, and this avoids some of the headaches of trying to bootstrap within the same address space of the application itself. Next, I'll go through the design and implementation of Chameleon. Chameleon has several goals for its design and implementation. The first is Chameleon wants to continuously re-randomize applications with a small enough period and a high enough entropy to make stack attacks probabilistically impossible. This means that even if an attacker is able to exploit a memory disclosure vulnerability, any information they learn from that vulnerability will be rendered pointless after the next randomization period. Chameleon should also transparently re-randomize applications. So existing code written in C and C++ should just work as is. Developers shouldn't need to worry about whether or not their application will be running under Chameleon's control. Finally, Chameleon should avoid complex self-hosting machinery and also be strongly isolated from the target application in order to prevent attackers from leaking randomization information. Next, let's talk about some of the mechanisms that Chameleon uses to achieve these goals. First, Chameleon needs metadata from the compiler describing how it's laid out each function's stack. While initially we thought we could use dwarf debugging information, it turns out this is actually incomplete, especially as you turn on more optimizations inside the compiler. Instead, Chameleon uses Popcorn Linux's compiler, which inserts LLVM stack maps inside of the intermediate representation in order to generate stack layout metadata. Here we see an example of a stack map intrinsic which has been inserted inside the LLVM IR. As the IR gets lowered down into machine code, LLVM will generate metadata describing how it's laid out this function stack, and it'll put this information inside of the ELF binary. As an example here, this stack map has put the value max inside register 14. Next, Chameleon needs to be able to transparently control the target application to switch between randomization epochs, or different sets of randomized stack and code. First, Chameleon uses ptrace, or the process trace OS interface, to interrupt and resume the target application, intercept events in the target, such as signals and fork or clone system calls, and reading and writing registers. Next, Chameleon uses userfaultfd in order to handle page faults in the target. In particular, Chameleon uses userfaultfd to serve newly randomized code to the target application on demand. This allows quicker switching between randomization epochs, as we don't need to bulk write the new randomized code into the target when switching between randomization epochs. Instead, the target application will page in that code on demand. Finally, Chameleon uses the proc file system, and in particular the mem file, to bulk read and write memory inside the target application. In particular, Chameleon uses this to serve the transform stack after randomization to the target application. Chameleon uses also Creu's libcompel to inject parasites into the target application for initial bootstrapping. Userfaultfd has some restrictions on which virtual memory areas can be attached, so Chameleon uses libcompel to remap that code memory inside the target to be compatible, and then creates a userfaultfd file descriptor, which is then passed into Chameleon to serve subsequent page faults. More information about this can be found in the paper. Next, let's talk about Chameleon's architecture. So on the right-hand side of this figure, we have the target application, and on the left-hand side, we have Chameleon. And these are in separate processes as denoted by the vertical dotted line. Inside of Chameleon, there are three main components. There's the scrambler, the event handler, and the fault handler. The event handler is responsible for interacting with the target application. It interacts with the target application through the ptrace interface and reads and writes that thread's state. It also receives signals about the target application, such as fork or clone events or signals inside the target. The scrambler thread is responsible for generating the randomized stack layout for every function and rewriting the code to match. The scrambler runs asynchronously with the event handler and fault handler and the target application, so we can overlap generating the next set of randomization while the application is currently running with a single set of randomization. Finally, the fault handler is responsible for serving code pages to the target application. It receives page fault events from the userfaultfd file descriptor and passes the randomized code pages through the kernel to the target application. The scrambler is responsible for randomizing every function's stack layout. On the left-hand side, we can see the frame's layout as generated by the compiler. Notice how everything is packed and there's a certain ordering of how things are laid out. On the right-hand side, we have the randomized layout generated by the scrambler. Notice that most of the frame has been randomized in terms of both the ordering of elements on the stack and the amount of padding added between different elements. Chameleon is able to randomize almost all parts of the stack frame, including the saved return address, saved frame base pointer, saved callee registers, and any local variables. The only part of the stack that is not randomizable is the arguments area to called functions, as this will require changing the calling convention of both the callee and the caller. We leave this as future work. In order to be able to randomize the different layout here, including the saved return address and all the callee saved registers, Chameleon modifies the Popcorn Linux compiler to insert extra no-op instructions so that Chameleon can insert extra code which will add padding. More details can be found in the paper. Let's talk about how the event handler uses the randomized function layouts generated by the scrambler and switches the target between randomization epochs. The event handler thread periodically interrupts the target to switch to a new randomization epoch. So periodically, the event handler thread wakes up and interrupts the target and reads its current execution state. So it reads through the ptrace interface and through the proc file system the registers and stack of the target thread into Chameleon's address space. Next, the event handler thread uses the scrambler's information and remaps the previously randomized layout into the next randomized layout. And it does that by mapping through the state transformation metadata emitted by the compiler. The event handler thread walks through the target's entire stack and rewrites it from the previous randomization to the next randomization. It also rewrites the registers. Finally, the event handler thread puts that information back into the target. It uses, again, the ptrace interface and the proc file system. The last step of switching between randomization epochs is to drop existing code pages. So as can be seen here, the target has been executing using the previous randomization. So we need the target to pull in the newly randomized code in order to match the new stack layout. So we induce the target using a parasite to drop existing code pages using the mAdvice syscall. This tells the kernel that those pages won't be needed, and the kernel subsequently drops them out of memory. Finally, let's talk about how the fault handler serves code pages to the target application. At startup, the fault handler registers the target code region with a userfaultfd file descriptor using the previously mentioned parasite through libcompel. It registers to the kernel so that the kernel knows any page faults inside the target process within the code page region should be sent to Chameleon. It then hands the file descriptor back to the fault handler, which can be used to deliver page fault events and the pages to the target application. So after the target has been executing for a while, it's got some code pages mapped in. So an individual code page fault happens like this. The target application touches a particular code page, creating a page fault. So for example, here, there's a page fault on the page containing the address hex dead beef. The kernel handles that page fault and realizes that it's registered to the particular userfaultfd file descriptor inside Chameleon and delivers an event to the fault handler thread through the userfaultfd file descriptor. The file descriptor knows it needs to serve the page containing that address, and it does that by sending that page down into the kernel through the userfaultfd file descriptor, and then the kernel maps that page into the target's application space. In this way, we can serve randomized code to the target transparently. Next, let's move on to the evaluation section. Chameleon was evaluated on a platform containing an Intel Xeon 2620 V4. This CPU has 8 cores and 16 threads. It has a 2.1 GHz clock speed with a 3.0 GHz boost, and the platform contained 32 GB of DDR4 RAM. Benchmarks were run on Linux 4.9 using Clang LLVM 3.7.1, which is the Popcorn compiler version. We use benchmarks from the NASA Parallel Benchmark Suite and Spec CPU 2017. For re-randomization periods, we use 3 separate periods of 100 milliseconds, 50 milliseconds, and 10 milliseconds. Decreasing re-randomization period means more frequent re-randomizations. Finally, we configure Chameleon to use a maximum inter-slot padding of 1024 bytes. First, we wanted to evaluate Chameleon's ability to inject entropy into the target applications in order to prevent attackers from guessing where stack slots are located. On the x-axis, we have benchmarks, and on the y-axis, we have number of bits of entropy. This corresponds to the number of bits of entropy on average per stack slot across all functions in each benchmark. As can be seen here, Chameleon injects a significant amount of entropy. In particular, on the spec benchmarks, Chameleon injects on average 9.17 bits of entropy per stack slot, and for the MPB benchmarks, it generates 9.03 bits of entropy per stack slot. This means that, for example, if an attacker wants to corrupt 3 separate stack slots in a single benchmark, an attacker has a probability of 7.45 times 10 to the negative 9 of guessing those stack slots. This makes it extremely difficult for attackers to guess the locations of stack slots in order to launch attacks. Next, we wanted to evaluate Chameleon's ability to disrupt gadgets as part of the code rewriting process. Here, we delineate between trivial and non-trivial gadgets, where trivial gadgets are only a single instruction, such as a jump or a call, and non-trivial gadgets have multiple instructions. We found gadgets in the separate benchmark binaries using the Ropper tool. Here, we see that Chameleon is able to disrupt a significant amount of gadgets. For the spec benchmarks, it's able to disrupt 58% of all gadgets and 78% of non-trivial gadgets. For the MPB benchmarks, Chameleon is able to disrupt 55% of all gadgets and 75% of non-trivial gadgets. This means attackers are likely to encounter a gadget that has been rewritten as part of the stack randomization process. Finally, we wanted to evaluate the overheads imposed by running target applications under Chameleon's control. Here, on the y-axis, we have slowdown in percent versus running without Chameleon's control. We have 3 sets of bars here, which correspond to re-randomization periods of 100 milliseconds, 50 milliseconds, and 10 milliseconds. As can be seen, Chameleon adds very little overhead to normal application execution. For the spec benchmarks, for 100 milliseconds and 50 millisecond periods, Chameleon adds less than 2% overhead. For the MPB benchmarks, Chameleon adds less than 1% overhead for 100 milliseconds and 50 milliseconds, and less than 5% overhead for a 10 millisecond re-randomization period. For the spec benchmarks, 10 millisecond re-randomization incurs a significant cost of 18.8% overhead. We will discuss this in the next slide. Overall, though, Chameleon adds very little overhead to application execution, meaning it's feasible that applications could be run under Chameleon's control in production. As part of Chameleon's overheads, we also wanted to evaluate how long it takes Chameleon to switch between randomization epochs. Here, on the y-axis, we have the transformation time in microseconds of a single switch. This includes interrupting the target, reading its execution state, transforming it to the next randomization epoch, and then writing its execution state back into the target, and finally dropping code pages from the previous randomization. As can be seen here, Chameleon is able to complete this randomization epoch switch very quickly. For spec benchmarks, it takes on average 335 microseconds for an epoch switch, whereas for MPB it takes 250 microseconds. Spec takes a little bit longer because it tends to have deeper execution stacks. There are several outliers here though. These outliers are caused by waiting on the event handler, waiting for the scrambler to finish generating the next randomization epoch. So this is a possible area of future optimization for Chameleon. Finally, we evaluated how much it costs Chameleon to handle a single page fault. It takes Chameleon on average about 5 microseconds to handle a single page fault, which worked out to about less than 0.1% overhead across the benchmarks. Overall, Chameleon is able to provide strong security benefits with low overhead. Chameleon generates about 9 bits of entropy per slot in the benchmarks we evaluated, and it also disrupts approximately 76% of non-trivial gadgets. Chameleon has geometric mean overheads of 0.7%, 1.1%, and 9.1% for randomization periods of 100 milliseconds, 50 milliseconds, and 10 milliseconds respectively. The randomization overhead was hurt by the scrambler re-randomization latency, however, because the event handler thread has to wait for the scrambler to finish generating the next randomization epoch before it can do the switch. This leads us to future work where we can increase the performance of this scrambler. Finally, let's conclude the talk. Chameleon is able to protect applications from stack-based exploits through continuous stack layout randomization. Chameleon randomizes stack layouts with high levels of entropy, making stack attacks extremely difficult. It's able to frequently re-randomize the target application with low overheads, and randomizes the target from an entirely separate process, which provides a cleaner abstraction and strong isolation between Chameleon and the target. There are several areas of future work, including performance optimizations for the scrambler, randomizing calling conventions in the argument area so there's no part of the stack that is set in stone, and extending Chameleon to other types of defenses, such as context-sensitive system call auditing or on-demand control flow integrity checks. Chameleon is open source and available at the Popcorn Linux website. Thanks for listening to my talk.